All right. Okay, so number one, you're just writing out your rules. Hopefully, you guys feel comfortable with all the rules that I'm asking you to memorize and to recall. Let's start with number two. Oh, and by the way, the old keys that you guys have caught a couple of mistakes with help some students just sending me some information of what they caught. So number two and parts of number three are incorrect, but as I go through, sorry, number two and four on the key are incorrect. So as I go through, I will highlight those issues. And also on my website, I just updated the updated key as well. So. Number two says object's position is given by f of t equals 2 sine squared 3t. Continuous differentiable between 0 and pi seconds. F of t is given in meters. Find the average velocity, or in other words, average rate of change from 0 to pi over 4. Average rate of change, average velocity has no calculus involved. You're just finding order pairs and finding slope, and that's it. Let me just rewrite the function, though, just to get it ready for the eventual derivative, and also makes it easier to plug in if that squared is in a more clear location. Okay, so let's find f of 0 and let's find f of pi over 4. I think on the key, I accidentally put a 3 here, so it should be squared. Sine is 0, 0, 0 squared is 0. 2 times 0 is still 0. Okay, so sine of 3 pi over 4. We know that's going to be, well, in that pi over 4 family, sine is going to be positive in the second quadrant, so root 2 over 2. Root 2 over 2, we can square that. Okay. So it ends up being 2 over 4, which is 1/2. 2 times 1/2, which is going to be 1. So your average rate of change, or average velocity, is just slope, change in y over change in x. Y sub 2 minus y sub 1 over x sub 2 divided, or x sub 2 minus x sub 1. Oops. Okay, so again, average rate of change, average velocity is just fine finding slope. All right, there's no calculus here. All right, so part B, at what point does the instantaneous velocity equal the average velocity? Set up the equation, but do not solve. This is basically rearranging of mean valley, or application of mean valley theorem. So this is what mean valley theorem says. Take the derivative, take the slope that we gathered, part A, and set them equal to each other. So we just have to find the derivative. That's where the instantaneous velocity comes in. That just means find f prime. The average velocity is just f of b minus f of a over b minus a. So instantaneous velocity, we got to find the derivative. To find the derivative, what's involved here? We got to use what? Got that bracket squared, right? Chain rule. All right, so outside's derivative first. If you want to find the full derivative of this expression, this is just power rule, bring down to 2. So 4 bracket to the first power. Keep the inside expression. Then moving on to inside's derivative, sine of u becomes cosine of u times u prime. So we have the instantaneous velocity here. We got the average velocity here. We're just setting them equal to each other. Okay, questions with A or B? Part C. When on the interval does f equals 1? So let's set that up. Here's the f of t function. All right, we want to first kind of begin to move things over to the other side. Eventually, you want to solve for t, but let's move what's easiest to move. Let's divide by 2. Oh, sorry, thanks. Okay, so dividing by 2, we can undo the square by taking the square roots. Plus or minus will fill up. If I did 1 over square root of 2, that's fine. But if you multiply top and bottom, if you rationalize the denominator, it makes it feel a little bit more familiar. This is basically going to be in that power 4 family, right? But let's go ahead and get that 3t by itself first by doing inverse sine Right? So in other words, this is basically saying, when is sine of theta equal to plus or minus square root of 2 over 2? Right? And because of plus or minus, you know that basically all four quadrants can be included. Right? Everything in the power of 4 family. Now it's only going from 0 to pi, but we want to go ahead and list out more than what we think we need, because that 3t is going to end up shrinking all the measures. Okay. Everything beyond this will be past the 2 pi mark, but let's go ahead, and what we can do is we can add 2 pi or 8 pi over 4 to these initial ones and see if they will fit, because we got to divide by 3t. So, or divide by 3. Okay, so 1 pi over 4 plus 8 pi over 4 is 9 pi over 4. 11 pi over 4. 13 pi over 4. And 15 pi over 4. I think dividing by 3, we can do that, but it just feels easier to not have to deal with complex fractions. So if I multiply by 1/3, that's the same thing. 1/3 times 3, we'll just cancel that out, gets t by itself. That's what we want. Multiply all the fractions together. 1 times pi is pi. 3 times 4 is 12. So pi over 12. Next up, 3 pi over 12. Which is pi over 4. All right, so these are out. Right, we only want to keep what's up to pi. 13 pi over 12 is more than pi. 11 pi over 12 is less than pi. So this is all we need. All right, any questions here? Okay, next page. All right, two cyclists are traveling on perpendicular roads. Cyclist A is traveling east. Cyclist B is traveling south. Find the rate at which distance between two cyclists are changing when x equals 8 and y equals 15. We know Pythagorean theorem will allow us to hit all three sides here. I'll call this x. I'll call this y. derivative. With related rates, we find the derivative of each variable or each term. And as soon as we find the derivative, we're going to attach a d over dt for that variable. Let's go ahead and list out all the variables that we have to make sure we include and involve. Okay, cyclist A travels east at 50 miles per hour. We know cyclist A is related to that x. Okay, so what would you say? We know it's going to be motion. It's not going to be just x. It's going to be the dx dt. So dx dt equals what? What's happening to this length? Negative, right? Not because it's going right or anything like that. It's because we can imagine that as A moves towards this point here, we can imagine this length getting smaller, and any dimension that's getting smaller over time, you want that rate to be negative. Okay, cyclist B travels south at 20 miles per hour. I know here, so what's happening here? What's happening to this length of the triangle? Getting what? Larger. Therefore, dy dt will be positive or negative?
Positive.
Positive. Good. I know that sometimes we may think, oh, south must be negative, but that could be true, but depends on the triangle, right? If the triangle looked like this, right? The triangle looked like this, and the B is going down towards this destination, and the triangle, then we can say dy dt is negative, right? But here in this case, dy dt is positive. Right? See that distinction there? Okay, so positive 20. Find the rate at the distance between the two cyclists. See how is that rate changing? So we're talking about dz dt, that's the unknown. When x equals 8, y is 15, Pythagorean theorem can help us find that z, a squared plus b squared equals c squared, ends up being z equals 17. Let's plug into the equation here. So 2 times 8 times negative 15 plus 2 times 15 times 20. And then 2 times 17 times dc dt. Next up, what is the rate of change of theta at that moment? You know you're looking for d theta dt. Before we get to d theta dt, let's build the trig equation that we can use. We can actually use any trig equation. You can use sine, you can use cosine, you can use tangent, because you have all 6 variables accounted for, right? There's no missing information. But in this case, I'm going to use tangent. The reason why is because that allows me to use the original set of information. Let's say I somehow messed up on z and dz dt, then my work could be right for sine and cosine, but it just makes it where the data is bad, so you're not going to get the right answer. So it's just safer to rely on what's given to you. So I'm going to start with tangent. So tangent of theta, we do opposite over adjacent. So in this case, it's x over y. We want to hold on to these variables because these cyclists are moving, right? Now, if these cyclists were just sitting still here, then we can use, but that's not going to be the case. Here, there's always going to be movement with the problems I give you, so you got to use variables here. Then you can use the constant, right? Then it'll become a power rule problem. But here, there's no choice but to involve quotient rule. Okay, so tangent becomes secant squared d theta dt. Quotient rule on the right side. This is my f. This is my g. Okay, f prime, x becomes 1. G is the y. Back to f. I'm sorry. We're doing related rates here. So f prime x becomes 1. That's true, but we need to include a dx dt. Back to f. G prime, y's derivative is 1. We're asking for y's derivative. Time is going to be the independent variable, so dy dt. All over denominator squared. Okay, we have everything that we need on the right side. We have dx dt, we have y, we have x, we have dy dt, we have y squared. So everything we just kind of transplant from part A. We're looking for starting for d theta dt. That's the unknown. So that's the variable that we want to kind of get by itself. And we want to make sure there's one last piece of information that we need, and that's not just theta, it's secant square theta. We want to find a replacement for secant of theta, and then we can square that ratio. So we can step to the side and build our second triangle. So at this moment in time, we know x is 8, y is 15, z is 17. So we can say secant of theta must be hypotenuse over adjacent. It's the reciprocal of cosine. Cosine will be 15 over 17. Secant will be 17 over 15. So we will take this, put it in here. Okay, so let's put everything in. dx dt gets replaced with negative 15, y gets replaced with 15, x is 8, dy dt is 20, y squared, that's 15 squared. Secant of theta is 17 over 15. Make sure we put down the ratio fraction first, and then we square it. So everything is accounted for. We just have to move things around to get that d theta dt by itself. We want to divide by 17 over 15. Dividing by 7 over 15 is the same thing as multiplying by 15 over 17. And the rest I just plugged in the calculator to reduce that fraction. You can leave it in that exact form, or you can write it as negative 1.332. Your units of measure, though, radians per time unit. So radians per hour in this case. All right, any questions? Okay, moving on to number 4. Okay, so number 4, want to point out that on the key that I set, I failed to keep track of that 2y. So I wrote cotangent of y, and that threw off all my answers. So I'll make that correction as we go through the problem here. Right, so 3 things here that we want to make sure that we include in our process. First is we'll see a bunch of y's here, so you know there's implicit differentiation going on here. Next up, we see x times cotangent of 2y. This is need for product rule here. And thirdly, there's that messy tangent raised to the 5th power with a square root over it. This is going to have to be chain rule. Let me just rewrite this to kind of get it ready for my derivative step. I know that this whole thing is going to be tangent of 5y squared raised to the 5 over 2. Got to take care of that outside and inside portion to get its full derivative. Okay, so everything is set up, hopefully. We can move into our derivative step. Let's start off from left to right here. We see product rule. We can take care of that. Okay, x becomes 1. G function. Back to f. G prime. Cotangent of u becomes negative cosecant squared of u times u prime. Okay, let me make sure that this makes sense here. Cotangent of 2y becomes negative cosecant squared of 2y times 2y's derivative. 2y's derivative is 2. We're asking for y's derivative, so we need to include the dy dx. Hey, by the way, we do need 3 dy dx to show up. We have 3 y variables. Each y variable will eventually produce its own dy dx. So the first one shows up here. Next up, minus y. The derivative of y is 1. We're asking for y's derivative here as well. So minus 1 dy dx.
Like for the cotangent to that, another one is we take u prime.
Well, this cotangent of 2y, we know it in the end, it will produce dy dx. So after we do its full derivative, we're just going to make sure we include the dy dx. Only one, that's right, yeah. But if another one shows up, you know something is not right, because if there's 3 y variables, but 4 shows up, you know something that's not lined up. Okay, left side of the equation is done. The right side, we have to take care of chain rule here. So outside's derivative, we'll do power rule for that outside portion. Okay, so 5/2 bracket to the 3/2. That's power rule. We keep the inside and the same. Multiply by the inside's derivative. Tangent of u becomes secant squared of u times u prime. 5y squared becomes 10y dy dx. And then and then we're done with chain rule for that. This whole thing is all connected. That's one thing. 3x becomes 3. And then the -7 goes to 0. I'm going to say -0 here, but you can just leave that out. You don't need to put a -0 here. Okay, I want to see that there are 5 terms in play here. You want to group all the dy dx terms together, all on the same side. So we want this together, this, and this, all on the same side. These are all separate terms. They all have dy dx. And then the non-dy dx terms, the ones I highlighted in red, are going to be on the other side. So we're done with the calculus. Now we're just adding and subtracting in a way where we can eventually get dy dx by itself. So here, in terms of cleanup, I'm just going to pull the 2, the x, and negative in front. Here, I'm going to multiply the 5/2 and the 10y to make it 25y. Okay, so as I move things around, I have 2 dy dx terms already on the left side, so I can leave those alone. This whole mess of a chain rule, I'm going to have to subtract over to the left side here. That becomes this. And then the cotangent 2y and the 3, I'm going to have it be together on the other side. From here, I can factor the dy dx out. Divide all this over. All right, next page, number 5. Okay, this one, this is already a function. There's no implicit here. We just have to find the derivative. The only thing that really should stand out to us is just the need for product rule here. But that's it. Everything else is just find the derivative of each individual term. But here we do have one of the new rules that shows up, inverse trig, that involve arc cosine here. Okay, x cubed becomes 3x squared. G function, the original, inverse cosine. Back to f. G prime, inverse cosine becomes, we know the derivative for inverse cosine looks a lot like arc sine. U prime up top with a negative, and then square root of 1 minus u squared. Oh, sorry, you're right. I found the derivative there. Thanks. Okay, our cosine. We have our u value being pi x, so the derivative of pi x would just be pi. Make sure we keep that negative in front. And square root of 1 minus u squared. My u value is pi x. We want to make sure we square that entire expression. Okay, done with the product rule. Moving on, secant derivative is secant u tangent u times u prime. And then 5 pi e squared. This looks like maybe we got to do power rule here, but what do you notice about all these terms? There's no variable, right? So there's no variable. That's a constant. What's the derivative of a constant here? 0. Okay, number 6. I've got to put a t in the equation here, so it should be 2 cosine 5 pi t over 2 equals 1. We want to solve for t. So divide by 2, take the inverse cosine. Okay, so we divide by 2, that becomes 1/2. Take the inverse cosine. Inverse cosine 1/2. We can move towards explaining that expression. We ask ourselves, where is cosine of theta equal to 0? sorry, cosine theta equal to 1/2. So we know it's going to be in that pi over 3 family in the first and fourth quadrant. So pi over 3, 5 pi over 3. I just want to make sure that I have enough. So I'm going to keep adding 2 pi to my original first and fourth quadrants. So pi over 3 plus 6 pi over 3 is 7 pi over 3. 5 pi over 3 plus 6 pi over 3 is 11 pi over 3. I keep going. Add another 2 pi, I get 13 pi over 3. Add another 2 pi, I get 17 pi over 3. Now, I want to solve for t, so I got to divide by 5 pi over 2. But dividing by 5 pi over 2 feels messy with all that complex fraction, so I'd rather multiply by the reciprocal. So 2 over 5 pi is what I want to distribute everything through. And the whole idea is that we can get that t to be by itself. And this does make that happen, because if I were to multiply this out, the 2's cancel out, the 5 pi is canceled out. I'm left with t. 2 over 5 pi times pi over 3 gives us 2 over 15, because the pi's cancel out. One's in the numerator, one's in the denominator. Here we get 10 over 15, which is 2/3, 14 over 15, 22 over 15, 26 over 15, and 34 over 15. Now we want what's between 0 and 2, and 26 over 15 is still less than 2, but 34 over 15 is more than 2. You know, 2 is, in terms of denominator, a term in the denominator will be 30 over 15, right? So this is going to be slightly less. This is slightly more. Oh, you mean 5 pi over 3 to this? First row. Ask your question again. Mm-hmm. No, that's right. So the initial ones, I'm just using my unit circle knowledge. Where is cosine equal to 1/2? Pi over 3 and 5 pi over 3, right? First and fourth quadrant. Yeah, so these two, I'm just using unit circle knowledge, and after this, then I added 2 pi to get additional ones. Okay. Okay, curve sketching. Okay, our function on the interval from negative pi to pi. Let's start off our process by finding f prime. One half x becomes 1/2. Cosine becomes a negative sign. To find our critical points, we set f prime equal to 0. Okay, we ask ourselves, where is sine equal to 1/2? In the first and second quadrants is where sine is positive. It's going to be in that pi over 6 family. Oh, sorry, my bad. This should be negative. So third and fourth quadrant, 7 pi over 6, 11 pi over 6. Now, we see that both of these values are not quite inside this interval here. We can find ones that are closer, that are going to fall inside the interval, or at least try to find ones inside the interval by subtracting 2 pi. Okay, we have our critical points. These both land inside the interval. So here's my slope sine line with my endpoints included. Okay, the ones I give you here will have alternating signs. So I'm just going to choose one to test. You can also tell by looking at your calculator, if you were to sketch this graph, you're going to see the graph is going to have three separate directions here. So if I plug 0 here, 0 looks like the easiest one for me to test. If I plug 0 into the derivative, 1/2 plus sine of 0, sine of 0 is 0, 0 plus 1/2 is 1/2, so positive slope. We know we're going to alternate slopes here. Okay, looking at the arrows here, we can definitely tell there's a relative maximum here, a relative minimum here. If I want to find the order pair, plug back into the original function here. Cosine negative 5 pi over 6, you know negative 5 pi over 6 came from 7 pi over 6. Cosine of 7 pi over 6, third quadrant, cosine is negative. Be negative root 3 over 2. There's the y value of my relative max. You know there's a relative minimum at negative pi over 6. Back into the original function. You know, cosine of negative pi over 6, negative pi over 6 came from 11 pi over 6. So let's think about from that perspective. Cosine of 11 pi over 6, it's going to be fourth quadrant. We know cosine is positive in the fourth quadrant. So positive root 3 over 2, but there's a negative here already. So I'm just going to keep that negative. Okay, second derivative. F double prime. F prime is 1/2 plus sine x. 1/2 goes away to 0. Sine becomes cosine. So F double prime is just cosine. Set that equal to 0. Where's cosine equal to 0? At pi over 2 and 3 pi over 2. Pi over 2 is safe. It falls inside this interval, but 3 pi over 2, let's find another coterminal angle. We can subtract 2 pi here. Okay. We have our critical points. Place them onto my second derivative sine line. Endpoints. Okay, I'm gonna choose an easy point to test. Let me test 0, see what the second derivative value is, because then I can determine what concavity I'm dealing with. Cosine of 0 is 1, that's positive, so concave up. My concavity is going to change here. Okay. Confirm there are 2 points of inflection. Plug these back into the original function. One half times negative pi over 2 minus cosine of negative pi over 2. If negative pi over 2 feels unfamiliar, look to where it came from. It came from 3 pi over 2. You know, cosine 3 pi over 2 is going to be 0. I get negative pi over 4 minus 0. That's just negative pi over 4. Okay, f of pi over 2. Back into the original function. Cosine of pi over 2 is 0. So I'll get pi over 4. Okay, so we have the most important ordered pairs here. We have relative max, we have relative min, we have our points of inflection. All these can go into your calculator for you to help you decide where those order pairs go. And one more set of order pairs to look for is your endpoints, so that you can kind of know where your point, where your graph is starting, where it ends. So you can plug negative pi and pi. You know, those are endpoints because that's what's given to you back into your original function. See what that gives you. 1/2 times negative pi minus cosine of negative pi. Cosine of negative pi, same thing as cosine of pi. That's going to be -1. Negative and a negative makes positive for both cases. And then everything else is just reading off of your sine line, making sure that you can list out all your order pairs and points of inflection, and your intervals of concave up, concave down, your intervals of increase, decrease. Make sure that you're comfortable with all the because statements. And they can get a lot of assistance from your calculator in terms of plotting those order pairs. But, you know, when it comes to this, just ballpark values. I'm not going to be looking to see, oh, looks like you're a little bit too high and your decimal is off. Okay, I'm just looking for, it should just match your basic shape of your graph. Okay, let me come around and see if you guys have any questions for me. Just find high scores. I know. What? So this is my lowest one. So that's why I have to. Right there. This is my highest one. That's why I'm. Huh? Yeah. It's pretty good. Well, I mean, you can tell by all your order pairs that you gather. Just compare them. What's the highest decimal? What's the lowest decimal? Highest of your absolute max. Lowest of your absolute min. No. I need to see this. No, on this, you can use your decimals to help you approximate on the graph. But I'm looking for this.
Like,
I want to do this by sort of. Now there's a. It's like they can get calculated small number. I mean, find the absolute max up here. Usually no. It's like extreme value theorem. You got to consider your endpoints and your critical points. Or another way to think about it is this: your absolute max or absolute min has to be one of these 4 locations, right? It's got to be the endpoints or relative max, relative min. It's one of these 4. The calculator will help you decide what the highest was. Thank you so much.
There's a phones. That's just like.
You read Texas. You read Texas. Yeah, you want to 36. Don't worry about that because. I know. It's got time we can work on it. Right. It's not enough. Oh yeah. No, it's 4 lines. You're driving. Sorry. Oh, that's the X value. I think I'm 2 plus 1 is a Y value. Which is whatever the decimal.
Who's good calls?
I don't
Yeah.
It doesn't.
So let's say -4 to 4. Now pick graph again.
Oh, you don't go back.
No, it's pick graph.
Oh.
Yeah. Okay, so, you can find that point there for second.
Good, that's.
Maximum.
No, you're gonna do.
Particle motion, maybe we got. And it's particle motion too.
Oh, yeah.
He's bonus, but still, yes.
Yeah.
Okay, how about this?
I didn't shoot. I think it was like.
You know that, that's your Y value. These are all your 4 Y values here.
Maybe they're back some particle.
That's, we have to know 12. These are your 4 Y values here. A negative pi is gonna be this. And negative pi over 6 is gonna be this.
Yeah.
And negative pi over 6 is gonna be this.
It's like
And
Cowboys.
pi is gonna be this.
At home.
So you can plug this in the
Hopefully
calculator.
it's gonna keep it.
Get that decimal value, get that decimal value. Get this decimal value.
Yeah, they won't, maybe it goes like 20 minutes.
The highest decimal value that you're gonna see.
They're only better at home, but like still.
Where's the highest decimal
My
value?
favorite home team.
This one right here. That highest decimal value.
I'm glad I went. I wouldn't want
That's
to.
that's matched it by.
Or Michigan.
Morning.
I don't know if I'm ready for this. I don't know if I'm ready for this test, though, but.
Yeah, we did 4 days of review, so hopefully that, you
Yeah.
know, all that practice.
So how herb sketching is one word.
This is light. I got them. Wait.
You do-
wait,
you said-
you-
For the.
Oh, wait.
Oh, you only tested.
Because it's just two times.
You live rates too.
It's like, it seems hard. Yeah.
Yeah, I'll be on.
It is, light, it is.
So cosine is log.
I forgot. Isn't it? I remember you doing.
Oh, that's what it is.
It is?
This.
I don't know.
Things stuff. It's still being looked at. You go to our. What it look like, natural days on us for you, the next.
I know you did the, you kind of do them.
Excellent. It's A to U, that's natural log of A.
Same thing.
Yeah, this is stress.
It's not, you said it's gonna be on. It's sine of data. Arm motion.
It's light.
This.
Like, why did I get
This, you don't want to do that. It's not that hard, it's just.
No.
But this guy's already put back up in there. You can go ahead and pass the test out now. No.
I can't like get it off back. I think I'm ready to that bill tomorrow. I don't know like Wednesday. That's it. I looked for all the time. But we're taking it to point.
What's the derivative?
You prime over.
Well, and then. There's no way to get time something for that.
Wait, can we just choose? We don't have like specific classes, right? It is.
Love you guys. Very much rooms. It's the part.